Hi everyone. In this video, we'll introduce the concept of improper integrals. So what is an improper integral? I'll provide the full definition later, but one example is the integral you see here, where the upper integration limit is infinity. But is it possible to make sense of an integral like that? Well, the problem with doing so would be that we can't ever actually reach infinity. But we can at least approach infinity. So maybe if we somehow made use of limits, then we might be able to form a definition of what this integral means. So here is the correct way to do it. Whenever we want to take an integral from a to infinity, we instead take the integral from a up to a value that I'll call t. It doesn't have to be called t, but I'm just giving it a name. And then if we were to let t approach infinity, which could be indicated by taking this limit, this would basically be what we mean by the integral from a to infinity. So let's try an example. Here we want to integrate this function 1 over x squared from 1 all the way up to infinity. Since we can't actually get to infinity, we instead go from 1 up to the value that I'll call t, and then let t approach infinity by applying this limit. You can visualize what's going on here by thinking about the graph of 1 over x squared. When we integrate from 1 to t, what we're really looking at is the net directed area under the curve in that interval. And then when we take the limit as t approaches infinity, that has the effect of moving the t value further and further to the right so that our area gets larger. The integral from 1 to infinity then might be thought of as the area of a region that goes on forever. And when you think of it that way, you'd probably expect that this area must be infinity, right? But be careful. Sometimes what we expect is true isn't what's actually true, especially when it comes to mysterious concepts like infinity. So instead of making assumptions, let's go through the details of calculating this integral correctly according to the definitions that I've given here. So to start with, let's focus on just calculating this integral from 1 to t. Once we've found it, then we can worry about taking the limit. First, we need to find an antiderivative, which is easiest if we express 1 over x squared as x to the minus 2. Because then we can simply apply the power rule to get our antiderivative. Next, we plug in our integration limits. So plug in the upper limit, which is t, then plug in the lower limit, which is 1, and subtract these results. After simplifying, we can see this as minus 1 over t plus 1. With that, we've successfully calculated the integral from 1 to t, but we still need to take the limit as t approaches infinity. So we apply this limit to the result that we just found. Now let's try evaluating this. And to do that, we just let t approach infinity and see what happens. We can see that the first term will approach 0 since the denominator is getting larger. And so our final answer will be 1. This might be a surprising result since it suggests that the area of a region that goes on forever is only 1 square unit. But just because it's surprising doesn't mean that it's incorrect. What's really happening here is that in the long run, the graph of 1 over x squared is getting so close to the x-axis that the amount of additional area we get by letting t go to infinity ends up being negligible. In any case, hopefully this example showcases the dangers of making assumptions about infinity rather than checking all the details carefully. The problem we just worked on showed an example of an improper integral, but more generally, an improper integral is defined as you see here. It is an integral that has at least one improper feature. So then, okay, what do I mean by improper feature? I like to describe them as unreachable points. An infinite integration limit is an example since we can never reach infinity. It is unreachable. Discontinuities also tend to represent points which are unreachable, since the graph typically approaches them but never actually reaches them. So they too are considered improper features. Regardless of the type of improper feature, we can use the same method to fix the problem every time. Just approach the unreachable point by using limits. Let's consider this example. The integral you see here doesn't have an infinite integration limit, but it's still considered improper because 1 over x has a discontinuity at x equals 0. Since we're integrating from minus 2 to 0, and since x equals 0 belongs to that interval, this is considered an improper feature. So instead of integrating from minus 2 to 0, instead we integrate from minus 2 to another number that we'll call t. After all, we may not be able to reach 0, but we can at least let t approach 0 to achieve something similar. But we can say even more than that. Because we're going from negative 2 up to 0, we can assume that t is a number which is less than 0. And that means t only needs to approach 0 from the left. This might seem picky, but in some situations you might actually get a different result depending on which side you approach from. So in order to get the correct answer, you should always consider what side you're approaching from when you spot an improper feature. Now that we've set this up, we can calculate this by finding an antiderivative. We know the antiderivative of 1 over x is ln x with an absolute value, and then we can plug in our integration limits. So plug in t and negative 2 respectively and subtract the results. Note that negative 2 will become positive 2 after the absolute value is applied, so I just skipped straight there. And don't forget that we still need to calculate this limit. To do that, we let t approach 0 from the left and just see what happens. Now, it's really important that we're taking the absolute value here because it's going to change our small negative number into a small positive number, which allows us to actually take the logarithm. After all, we can't take the log of a negative, we can only take the log of a positive. So then what happens when we take the log of small positive numbers which are close to 0 like this? Well, we get a result which approaches negative infinity. To convince yourself of that, you can refer to the familiar graph of ln of x. Now, subtracting ln 2 isn't going to stop this from going to negative infinity, and so with that, we've found our answer. Notice in both the examples we looked at so far, the limits we ended up with were easy in the sense that they didn't end up being indeterminate. Of course, it is possible that could happen, and if it did happen, then you might need to consider a method like L'Hopital's rule to get your answer, but fortunately that wasn't necessary in the examples we've looked at so far. When describing the behavior of an improper integral, it's common to use the words convergent and divergent. So let's talk about what those words mean. An improper integral is called convergent if it results in a finite value. Otherwise, it's called divergent. Divergent essentially just means the integral results in an infinite value, or it could also mean that the value of the integral doesn't exist. The first example we looked at in this video resulted in a finite value of 1, so we would describe that integral as convergent. Our second example, on the other hand, resulted in this infinite value, so we would describe that as divergent. That's it for the basics of improper integrals, but so far we've only worked on examples that have an improper feature at an endpoint. So what if we had a discontinuity, say, in the middle of the interval? Or what if there was more than one improper feature, maybe one at the endpoint and one somewhere in the middle of the interval? Well, for those types of questions, you can refer to the next video, so look forward to that, and I will see you next time.